Hello to the international chapter of the Pirate Party's Working Group for Energy Policies. Today we will hear a talk about heat storage and accumulators from Dr. Franz-Josef Schmitt from the Institute of Physics. He is at the Martin Luther University in Halle, Germany. Better known for us as FJ, he's also chairman of the Pirate Party Berlin. We will record this, so if you have questions later, you can stay anonymous just if you type your questions in the text. And with this, hello, FJ, and the stage is yours.
Hello, thank you very much for the introduction, Fredo. I really like this topic because a large part of the energy consumption in Germany is heat. So we have cold winters and we always think about electrification, so electricity. Why not store the heat directly? So my topic today is heat storage and accumulators. It means techniques for storing heat. I will talk a bit about the available physical methods and point out one special method, that is latent heat. I will, of course, also talk about the possibility to exploit sun energy in form of heat, not photovoltaics, directly thermal solar. And yeah, it's not like, let's say, a table of content which is followed in a sequence. In each step, we will look a bit at the balance of energy and the costs of this technique. Just to start, we think about a regular house, which is hopefully soon having photovoltaics everywhere. And it might also make sense to have photothermal, solar thermic installations, because we will see that this has a very nice coupling efficiency, and we gain a large amount of energy per square meter if we use the heat directly. And in a well regenerative energetic house where everything is nicely using photovoltaic energy, heat, we might have electric cars, circuits that connect also the electric energy from the solar panels with intelligent charging systems, maybe a heat pump for the heating. Then we have the heat directly, which goes to a kind of storage tank here. And we also have a wastewater handling, so wastewater is also reused in some way. And this idea to have zero energy houses or even negative energy houses is something which comes to the reach. And this is my point today to show how we can reach this. There are already cities, also countries in Northern Europe, Sweden, Finland, they are very progressive here, Denmark, but also Switzerland. Here in Switzerland, we see a heat storage system driven by a water tank. This is practically only water standing in Perlen in the region of Luzern in Switzerland. And just to look at the description, it's a 33-meter high tower containing 5 million liters of water. So 5,000 tons of water, which are heated up to 145 degrees. And from that, we can store 400 megawatt hours of energy. So these are 400 kilowatt hours. And I would now like to introduce a bit the units. I regularly use kilowatt hours because it's easy to compare it with electric energy. Of course, you can also speak in megajoules or something, gigajoules, but that's maybe more complicated to compare. Yeah, we all know a kilowatt hour of electric energy is maybe, depending on the contract, you have 30 cents. So we can also easily calculate this. In heat, in the form of heat, it's cheaper, of course. It's maybe 10 cents per kilowatt hour. So we immediately can also see the price of this energy. So we can store energy which costs in form of gas on the market 40,000 euros in this tank. With this energy, we can heat a regular flat of 150 square meters for 5,000 days, or let's say what makes more sense, maybe 500 flats for 10 days. This is a heat storage tank to bridge cold days. and bridge also the so-called Dunkelflauten, when maybe there is not enough electric energy to drive heat pumps directly. When you really need nearly 100% in deep winter, you can store some heat directly to overcome these pretty cold days. The investment cost of this system was 5 million Swiss francs. So Schweizer Franken, 5 million. That's about 12 US dollar per kilowatt hour. And if we look at the price of batteries storing electric energy, this is pretty much smaller. So batteries now in the private sector, $200 per kilowatt hour, in the industrial sector, $50 per kilowatt hour. So even comparing to the industrial, we are a factor of 4 cheaper. But we will see that is by far not the end. We end up much cheaper with modern, also easy systems. Especially smaller systems are already also available even cheaper than this 12 US dollars per kilowatt hour. Here we would need an investment of $100,000 for our flat. That sounds much, maybe 30 years to amortize, but we will see it's already possible cheaper. And just to start with such values here, coming from a real installation done in 2022 in Switzerland. This is not absolute nonsense. Of course, in an industrial scale, it's used to bridge cold days. And I would like to shift this talk in a direction to say, does it make sense to install such a thing, or a smaller thing, of course, in a private household to be completely energy independent? So we are complete independent from any energy source. And of course, we can already do so by storing electric energy with accumulators. But we will check if it's maybe possible to reach that goal cheaper when we store the heat and what's necessary to do so. So even if this would take 30 years to amortize, it has 0 emissions. It's a one-time installation, which might have a lifetime much longer than 30 years because it's just a big water tank, and we are complete independent from any energy source. So whoever is thinking, okay, this is interesting, can now follow this talk and be sure it's already much better if we look at the techniques available just today. Other techniques don't use water, for example, but sand. Here we have the largest sand battery driven by a company, Polar Night Energy. They have these industrial installations here in Finland, which is not principally something different to water. It depends on the heat capacity in these systems. Sometimes it's more pragmatic also to use sand. Sand can be heated up further. It's not only possible to go to 140 degrees. You can go up to 400, 500 degrees. But it's also called a seasonal direct heat storage. We will look a bit about these different types. One type is what everybody has at home, the heat water storage tank. So everybody having a heating at home also has a heat storage tank for warm water, can be 50, 100, 150 liters. We can look at buffer storage tanks. They are pretty similar, but they are not only used to store warm water, but maybe also heat during a night. There are combination storage tanks for both, of course, because it's the same technique. But the interesting thing I will focus on is the seasonal storage tank that could overcome the whole winter period. And one special technique, the latent heat storage tank, that could in principle store heat for several years, not only for one winter period, but even for 5, 6, 7 years. And the suggested technique will be that we collect heat from sun. This heat is exchanged in a tank. So we have a water storage tank, and then it could be directly used for heating. It could also be used to drive a heat pump. We will see that this is the much more realistic scenario. And of course, as a warm water for showering or bathing or whatever you need. These buffer tanks we have seen are possibly done as in form of water tanks. And of course, they would like, we would like to store the surplus, so the amount of heat we have in summer, but maybe also during production processes, during combustion, burning rubbish, everything generates heat, and this could be stored. And we could also do it in short-term periods, even in winter when we have at least light during daylight, but also in the seasons in spring and autumn when we might still have a lot of heat during the midday and need some of it in the night. The seasonal, of course, would try to overcome the whole winter period. And one thing that is already in production is the geothermal probes for heat pumps. So if you drive geothermal probes of the heat pump in the ground, you practically use your garden or the ground below as a form of a big heat storage. But you can already buy similar systems also for your household. Here we have a 3000 kilowatt hour system from the company Fenotech, and I don't get any provisions from them, so feel free to choose anything. It's a 35,000 liter tank and available for 18,000 euros in a time of 6 to 8 weeks. And this is already 1/3 of this 10,000 kilowatt hours we might need to heat a flat for a whole year. So we can already see, maybe also to underline it with realistic numbers, let's say your building is category B, you have a final energy consumption of 70 kilowatt hours per square meter and year, primary energy demand of 80 kilowatt hours per square meter and year. These are typical values, which can still go much better if the house is nicely insulated. It's something we will surely end up in the future due to European law. I, from my side, I hope that we can also accept lower categories if we just shift completely to regenerative energies, because I think a lot of money is used for insulations. It's also CO2 emissions rise due to insulation processes. This all needs to be compensated later on. If we shift directly to a complete regenerative energy consumption, we could also live with lower classes. But let's say this is a typical value for quite a new building actually, which is not too good in insulation, or an old building which is already insulated. Then this 70 will end up for 150 square meter in 10,000 kilowatt hours per year. Here we have a calculation for 180 square meters, that's 12,600. And a typical question for a physics student would be, how much water do you need to store such an amount of energy? The students should be able to find this value, 4.2 joules per gram and Kelvin. And of course, from that, one has to calculate between joules and kilowatt hours. So I will not follow this. Of course, I could present it if someone is interested, but this will end up in about 100 cubic meters, 100,000 liters of water. This is already somehow visible. I go back to slides from this tank. We need 10 liters for 1 kilowatt hour. So 3,000 kilowatt hours, 30,000 liters, 35,000. If we want the 10,000 or 12,000, let's not dig into the last digit after the points, then we need a bit more than 100 cubic meters. This is also available. This is a 10,000 kilowatt hour storage tank for private purposes from the company Fenotech. It has a bit longer delivery time. It's a special construction, and you will pay 38,800 euros. So we could, in principle, from that have our complete energy freedom, complete complete energy to be complete autonomous for 38,000 euros. And also here the price tendency is falling, not because there's a high technique like in microelectronics. The computer chips become more cheap and also solar panels become more cheap because the production is changing, the techniques make a progress. Here we mainly have the fact that at the moment these are unique constructions. So if the broad market would demand for such storage tanks, you could have them much cheaper. And it's easy to see that we end up here at about $4 per kilowatt hour. So as compared to the 50 for the direct electricity storage, we are around 10% of the price. And this might take 15 years to amortize, but only from the fuel cost. Only if you calculate the cost of your gas you will burn, and only for the price you have today. Today, for such a flat in the category B2C, 10,000 kilowatt hours, you will need at least 1,000 euros of gas per year. And this amortization, okay, it's not only the cost of the fuel, it's also calculating the cost of the gas heating itself, which is actually $20,000. But again, you will have zero emission. You are complete independent, and you just do it as a one-time installation. And if you install a heat pump, we will see it might make sense to do both, to have a heat tank and a heat pump. But the heat pump is also around 38,000 euros. It's actually funded. And if we have a possibility to keep the heat up in this direct heat storage, maybe we could even heat our flat without a heat pump. And this is something I would now focus in the second half of my talk, which is exploring the future option of a so-called latent heat storage. What does it mean? It means you have a change in the aggregate state of the medium. So if you have water will freeze at 0 degrees Celsius. And when water is freezing, it does not longer cool down, because the crystallization energy of the ice is practically pumping the energy into the medium, which is taken from the outside when it cools further down. That means you will stay at 0 degrees Celsius until the whole ice is frozen, whatever temperature you have outside. There might be some imbalance in the system, but in generally that's the case. And okay, what does it help? It's 0 degrees Celsius. You could also have wax, for example. Paraffin has a melting point of 60 or 70 degrees. So it means if you have a molten pool of wax and you would let it freeze, it means condense. The solid state will stay at 70 degrees until everything is solid. And these phase change materials, that's not only paraffin, also salt, hydrates, even water could be used. The only problem is that this is at 0 degrees Celsius, and they are still under development. Might be interesting candidates to keep your tank up at 70 degrees or whatever. Maybe you find something melting at 100 or 150 degrees. So you will stay in this temperature regime until the whole solidification process of your material is done. And here you have much lower losses than in hot water storage tanks. You also have a higher heat storage density. And you also could use ice if you use a heat pump, for example. For a heat pump, it could already be interesting to have 0 degrees Celsius, especially if it's outside, maybe -20. You can still pump with a factor of 2.5 between 0 degrees Celsius and 20, what you want to reach in your flat. It's pretty difficult to pump heat if you are at -20 degrees. So this heat exchange from our heat tank could be direct if it's warm enough, or it could be a heat tank which is driven in summer and then stored in form of an underground storage tank used as the heat storage for a heat pump. So here you would not need let's say 60 degrees, which is a minimum to drive efficient heating. If you have a fluid heating, maybe you could also work with 45 or 50 degrees, maybe even lower. But here even zero, even ice is already helpful if you use a heat pump. But of course here you need electricity. Here on this side, not, if it's really the direct heat you use. Let's look at possible heat tanks that use paraffin. Paraffin is of course much more expensive than water or sand. Here we end up at $600 per ton. And even if this is a bit smaller, if you take large amounts, it will finally end up at $100,000. So this is not yet cost effective at the moment. This melting enthalpy is similar to what you can take from water if you heat it between 0 and 100 degrees Celsius. About 240 kilojoules per kilogram. So 15 kilograms of paraffin can store 1 kilowatt hour of heat. So that again, we will need our 10,000 kilowatt hours. We need 150 tons. That's not yet cost effective, also a bit spacey. Practically you would need a pool of paraffin in your garden or something. But it points out that this is a general possible scenario. And then if you take this latent heat during the winter, you would not even need a heat pump, as your system stays at 60 or 70 degrees, depending on the material you use for the whole solidification process. Of course, there are already more intelligent systems, metallic zeolites as intelligent heat exchangers in the project ZeoMet, actually a research project in Saxonia. And to see where the energy will come from, I would like to now to look a bit at the numbers and our solar energy exploration. If we exploit solar energy with photovoltaics, we need a square meter for about 200 watt peak. And from that, we will get about 200 kilowatt hours per year. Here I should write per year. If we use heat directly, we will get about 1,000 kilowatt hours per year. We have nearly 100% absorption of the sunlight if we go directly to heat. But we will lose something if we go to a heat pump, because the heat coupling efficiency from the external to the internal system then is about 40%. So at the end, this is still twice as good as the conversion to photovoltaics, to electricity. It could be even better if we do not use heat pumps, but directly a heating in our flat from this storage tank. But the area you need on your roof to obtain the 10,000 kilowatt hours in 1 year is about 25 square meters. So it means practically everybody who has a roof, maybe not in a city where a building with 60 flats has only 100 square meter roof, but everybody who has his own roof could also become totally heat independent by using 25 square meters for direct heat exploitation. That means solar thermic installations instead of photovoltaics. So this is practically also already one of my final slides. I will summarize what we have in costs. The battery storage cost is actually 50 $ per kilowatt hour in industrial applications. Heat storage is actually available for $4 per kilowatt hour, plus a demand of 100 cubic meters volume to install such a tank. Might sound a lot, but yeah, it's practically 5 times 5 times 5 meters. Okay, the cellar is not 5 meters high, so maybe it's 7 times 7 meters in square and 2 meters high. So you could install it in a large cellar room, or you have it in your garden in form of a kind of pool. And what everybody could use and should use is that you use surplus of your photovoltaic energy, especially if you don't get money for it, to store heat. And that can be done with a 150-liter tank at home. Practically everybody has it on his heating. You can use it to store 10 kilowatt hours. So where's the problem? Yeah, why don't we do it? And I would like to cite Guido, who is leading this group here, the energy policy group of the Pirate Party. In the future, other people will earn money from the energy, and those who don't like that, and those who will not do that because they are now, of course, and they will lose. They will not like that. And that's why we hear a lot of wrong information in this field. A lot of people speak about problems to store energy. We see in other talks, we have heard other talks, that it's already possible to store electric energy with accumulators. We just need to discuss how much we need to install. But here I would like to give a little bit an additional idea of using heat storage system as a support to support the storage possibilities with a very simple and cheap technique. And for that, it's something we could do already. I just installed a heat pump in a house in Berlin, which is running pretty well, which reduced our primary cost in form of electricity instead of gas by 30%, and has a factor of 3.5, instead of nearly 40,000 kilowatt hours for the whole house with 4 flats. Our demand was 12,000 kilowatt hours of electricity last year, and I hope that a lot of people will follow, and thank you for your attention.
Yeah, FJ, thank you for the interesting presentation. I think it's a good option to know, or it's a good option to know that there is not only one solution for the problems we are facing, and storing heat is a very interesting addition to having batteries do the storing of electricity. Which of course is more versatile than heat, but if you already start with heat, then it makes sense to store it as heat if you have the technology to do that with a high efficiency. And as you presented, there are several options to do that. So one size fits all is probably not the best approach for the energy transition, and having multiple options that are fitting various applications is a very good option. So are there any questions from the audience?
I can add something to your comment, because from physical point of view, the losses appear in the conversions. Yeah? So always when you convert energy, you lose whatever you do. There's no technique which has 100% efficiency in a conversion process. And if you need heat, you can store heat. If you need electricity, you should store electricity directly. Of course, it doesn't make sense to store heat if you later want to drive a heat to power system to gain electricity from that. Then you use accumulators. And that's also a reason why it doesn't make sense, for example, to use hydrogen for your heating, because we have enough heat. We don't know where to get rid of the heat in the future in summer, and we should think about to shift this heat into the winter when we need it, which is a very cost-efficient process, because shifting heat is always more simple than producing from any fuels, whatever, hydrogen or whatever.
Yeah.
Dustin.
Hey, so I was just bringing up, I guess, consideration for manufacturing purposes with, I guess, thermal batteries that can reach up to higher temperatures, such as a refractory brick.
Yeah, there are some interesting approaches. Also, it's a wide field. So these sand batteries, they are sometimes already driven up to 600 degrees. In principle, you could use molten metals, which would work as a latent heat storage with a temperature of even 1,000 or plus degrees Celsius. Of course, it also depends what you need. So and how the cost is. So metals are quite expensive. Sand is a quite good approach, in my opinion.
There also is the option to combine the heat storage with a heat pump to get even higher in the temperature. And in some cases, you might not use the classic heat pump, but just use a system that heats up gas and then compresses that gas to get to a higher temperature level. So you have temperatures that you can use in industrial processes. So there are many options to utilize heat storage.
Mm. Yeah.
In principle, maybe one addition, it would be interesting, as Guido said, to work at lower temperatures and then use the temperature with the heat pump to still reach your goal, instead of storing too high material with too high temperatures, because whatever insulation you have, you will have a loss which is proportional to the temperature difference. So if you have a 100 Celsius medium and outside it's 0 degrees, you have only 10% of the heat flow in form of losses as compared to a 1000 degree system. And this is a crucial point if we talk about seasonal heat storage. Even in latent heat or also the general heat storage with sand or water, it is always facing a heat loss due to an energy flow. But this with a good insulation and a reasonable temperature, this can be reduced in such a way that you lose less than 1,000 kilowatt hours in 6 months. So that is not a problem anymore. Might reduce your bulk balance by about 10% over the year.
The thing to remember is that basically it's about storing energy. And the temperature, the absolute temperature, is basically secondary to the question of how much energy you can store and how efficiently you can store the energy. When you need a higher temperature, then use a heat pump and draw the energy from the storage. So that's flexible and should depend on the actual application.
Okay, thank you. That's good to know. I didn't know about that approach.
It's a quite common thing that people are not very precise in how they think about temperature. Temperature is somewhat diffuse concept after all. When you have a medium like when you have gas and you compress or decompress gas, then the temperature can change drastically. The energy content stays the same. That's the basic principle that heat pumps are using. They're compressing and decompressing gas to change the temperature while having the same energy content, but using that compressing of the compressing of the gas and producing higher temperature to take energy out of the gas. And so the same is with the storage. It's not about how what is the actual temperature of the storage is. The question is only if you have enough energy in it and if you have a mode to get the energy out of the storage. And as FJ presented, there are a couple options to do that. And I like the phase change storage the best, since you don't have a change in temperature, you only have a change in the state between 0 degrees water and 0 degrees ice, and you get a lot of energy out of that.
Yeah, and sometimes my students also, they ask that they have difficulty to imagine how a heat pump can achieve an efficiency of 300–400%, because they learn in an efficiency of 100%. Of course, they also learn the heat pump and the Carnot process and the inverse Carnot process, so they should know it. But some still have the imagination. Okay, best case is 100%, and then I tell them, okay, just have a simple imagination. The temperature is just the question which determines these efficiencies. But the energy you would like to transfer is inside the volume of gas and the particles. So if you, very simple system, if you open a window and outside it's warmer than inside, then the energy will come in, the temperature will rise without any need of electricity. You just need to open a window. That's a minimum. And this is exactly the scaling of this efficiency. If you have a bigger temperature difference, this efficiency goes down. But the heat transfer for a temperature difference of 0 is infinite. If you have no temperature difference between outside and inside, you can exchange an infinite amount of energy between both sides without any need for power. So you don't need any energy to do that. You just allow the system to diffuse practically.
Any more questions? Yes, go for it.
Sorry, I keep asking all the questions, but so in regards to creating the models for these, is there any open source models for particularly phase change types or simulation open source for people to, that we could use to teach people how to understand these systems, how to further develop them and collaborate with others to develop them, stuff like that?
Yeah, that's a very nice question. Of course, heat pumps can be simulated. There are platforms to do so. They are a bit technical and maybe a bit complicated. Maybe I can find something just now, which is a bit on the educational level. Yeah. Maybe it's not the best for heat pumps. I like these simulations of FAT. I show them at the University of Colorado. I show them to my students sometimes, but they're a bit more on the basic level. So what you can do here is to follow simulations for the diffusion processes of gas and the exchange of heat during these processes, and when you heat the system, how temperature develops in dependency of volume and so on. It's maybe not the easiest thing. I would dig something out where you can also understand the heat pump and maybe also a heat storage system a bit better, and deliver that then, I would say, later in the chat of the YouTube video or something. I think that's a good idea, that we offer tools for the people to better understand these systems. But even a physics professor, in principle, you can easily calculate the so-called Carnot process, and this is the basic process also for other machines like Stirling engines and so on, which are converting temperature differences to power, to work. They have an efficiency which is determined by the difference of the temperature between the hot and the cold side divided through the temperature of the hot bath. Yeah, what does it mean? If you have 0 degrees and 100 degrees, you have about 25% efficiency for that process, because you have 100 degrees difference, and you have to refer it to 400 degrees Kelvin. Yeah, we always have to calculate in Kelvin in that moment. And if you now want to do the opposite, you want to use electric energy to transfer heat, you just have the inverted efficiency. That means a factor of 4. And I always bring this example. Yeah, it's like you want to shift warm air. Somehow you have to compress it a bit so that it becomes even warmer and can radiate energy in the colder system. So you have to transfer heat practically from cold to warm. Yeah? That is something which does not happen automatically. Normally heat always flows from warm to cold. So how can you transfer heat from cold to warm? Outside it's a bit colder. We still want more heat inside, so we use the cold air outside, and then we compress it. It becomes hotter than our temperature inside and can release energy even inside. And this process does not necessarily need so much energy like the heat you transfer. If you have practically only 1 degree of difference, this is a pretty efficient process. And I think it's worth to find a good animation, good simulation for such a system, so such a problem, to explain it in more details.
Not 100% sure, but I think there is such an animation on Wikipedia.
It's at least something which is already explaining the basic problems.
Basic functionality of a heat pump. I mean, almost everybody uses heat pumps. Most of us have one in the kitchen. It's called refrigerator. It's just working the other way. It's keeping the inside of the of the refrigerator cold and transfers the heat outside into your apartment. And if you put the inside of the refrigerator outside your house, and you have a heat pump that's heating your house.
Yeah, the refrigerator is exactly the inverse Carnot process and the heat pump. So you could even use a refrigerator if you break a hole in your wall, and then you open the door of your refrigerator outside and have the radiator, the heat radiators on the backside inside, then you have practically a heat pump. Then you open the door outside, and the refrigerator will run as long as the set temperature is still colder than the temperature outside, and pump heat from outside to inside.
Yeah, that's one of the things why I think it's totally funny when people are telling that the heat pumps can't work. That's okay. Almost everybody has one. So, obviously,
okay.
it does work.
It's difficult to calculate the efficiency of your refrigerator. Of course, maybe some old also have a low efficiency, but I was pretty surprised when I was talking to a professor at University Halle, who explained me that he also believes this will not work. I don't know which party he is voting for. Maybe I don't want to know it, but so I told him. He told me in our temperature area, so in our Breitengrad, it cannot work as it's too cold in the winter. And then if we look at the Wikipedia article, I think it's not too nice in the simulations, but maybe I can share this screen shortly and show. Then we immediately find this very basic formula here for the heat pumps. That's the one I mentioned. You will always need to look at the temperature difference, and the temperature difference divided by, so if you take the inverse of this, you have the so-called Carnot machine. And this is, of course, always smaller than 1, because this difference is maybe only 0.1 or something. But this term, the COP of your heat pump, this coefficient of performance, that means the efficiency is always bigger than 1. So if this is 0.1, then this is roughly 10. Practically, in reality, you will not buy a heat pump with a COP of 10, but 4 to 5 is typical. And that's also reasonable, because here we speak about 20 or 30 degrees. So somehow, if you dig into the physics, it's surprising that you don't end up with higher values, that you have a limit at 4 to 5, which is pretty technically and not physically limited.
The easiest way to debunk that heat pumps wouldn't work in Germany, since it's too cold here, is the fact that in the Scandinavian countries, the heat pump is the leading heating method of homes. And I guess they have a little bit colder winters than we have.
Yeah, we see, let's say minus 20, plus 20, this would be 40 degrees. And here we have the 300 degrees Kelvin. So from physical point of view, even at a minus 20 regime, you should end up by a factor of 7 to 8. And here we can easily see this limit, 4 to 5, is mainly given due to further technical constraints and not limited by the physics behind.
That's the basic rule. You never reach physical limits with real-world implementations.
The most important part is actually that this minus 20 degrees, even in Scandinavian countries, is not that often. So yes, maybe then it's not super efficient, and yes, maybe you need more electrical power, let's say power in total, than you would run with another system, but that's only a few days maybe. That's not for months. So yes, 20 years or even 25 now or so. In the Scandinavian countries, it started with the heat pumps, and many did the system where they were drilling into the soil. They don't do this anymore because the heat pumps are so efficient now, and the inefficiency with minus 20 degrees or more is so rare that at least in the bigger cities, everybody has just a air heat pump.
And just to close the circle, it's exactly the point why I wanted to point out that even our 150-liter tank at home could make sense without a big investment to be used at a heat storage system, as we could shift energy from the day when we surely, especially on our roof, especially in Scandinavia, where we have sunny winter days, this roof surface temperature is not minus 20 degrees Celsius the whole winter long, and there we can also pump some heat, store some heat, even in the winter day for the cold nights.
Okay, I think that pretty much summarizes the whole thing. Basic thing is that yeah, we need to do stuff, and there are lots of options, and it's not like We have to wait for some magical technology that's going to be discovered sometime in the future. We already have all the technology that's necessary for the energy transition. We just have to do it. With that, I would say thank you again, FJ, for the presentation. The next session most likely is going to be a tandem session with the two of us about hydrogen. We're working on that, and we're going to inform you soon when we have a final date when that's going to happen. Thank you.
Thank you.